So under constant acceleration, the plot of acceleration versus time is very simple, and indeed the plot of velocity versus time is very simple because it's just a constant slope. But what's the position doing? Well, we start at a negative value on our diagram, so I'll have that there. So that will be our x0. Now if I'm going to write x0 on there, then I should write an x0 on here. Always have things defined on your diagram. And if we're going to be moving and we end up at x final at a later time. Now what's this shape going to look like? Well, it's going to start off at some slope. And the slope here is going to be the slope given by our initial velocity, which is u. So if we break this up into a small amount of time, delta t, then we know that the velocity is the distance traveled over the time. And so the distance traveled is going to be the velocity times the time, or u times delta t. And up at the end it'll work the same, except the velocity v is larger than u there, so the slope should be steeper. And somehow those slopes have to match, and so if we try and smoothly connect those curves, it's got to look something like that. Okay, let's do the algebra for that. So we know that the acceleration is constant, and we know the definition of acceleration. So it's the change in velocity divided by the change in time. And so the change in velocity is going to be the final velocity minus the initial velocity. And the time taken we've written down as just t. If we multiply both sides by t, so if we multiply the left by t and the right by t, it's going to cancel that. And so we'll end up with at equals v minus u, and we can rearrange that. The most common way of arranging that one is as v equals u plus at, just adding u to both sides. So that's the first equation we often remember when we're talking about constant acceleration. That relates the final velocity to the initial velocity and how much you're accelerating. It's a little bit harder to figure out where we're going to be because our velocity keeps changing. So let's just look at a particular time in the middle where we've got, say, a velocity v1. At that time, if we look at a very small amount of time, the velocity won't change very much. And so if we just take a small amount of time, delta t, then we know that the distance it's going to change is going to be delta x, is going to be v1 times delta t. And v1 times delta t is basically just a little rectangle that big. It's the area of that rectangle. And what we have to do is we have to have the little change in distance we get from that piece, and the little change in distance we get from that piece, and so on and so on. And that turns out to be just the area under this curve. That's how far we go. And again, you can do that formally by going to calculus, but if you just believe me that that's the area, and you can kind of see it, it's just the sum of all those little rectangles, then it's the area of this rectangle plus the area of this triangle. And the area of this rectangle, well, that height is u, and this length is t, so that's just u times t. And this height is v minus u, and that length is t, so this is going to be half of the product of those. So it's v minus u times t, that's the size of that big rectangle there. And because it's the triangle, we're going to have half of that. So we're going to have to add this area and that area together to get the distance that we travel. So the distance we travel is the final position minus the initial position. And we've just agreed that it's going to be this ut, the area of the rectangle, plus v minus ut all on 2, which is the area of the triangle. Alright, so I'm going to introduce a symbol which everyone else uses, which is just s, the total distance traveled. And then I'm going to plug this velocity here into there. In fact, it was particularly easy because we already had v minus u, so we could just go straight in and plug in our at. And that's the second equation we use to describe how things move under constant acceleration. And so we can see this curve here is quadratic because it goes as time squared. Now there's a third equation that people use, which is really just a rearrangement of these two. What we're going to do is we're going to try and eliminate time. And so from this equation here, if we divide by acceleration instead of by time, we get, and then we're going to plug that into here. So we just expand out the first bracket and then the second bracket. And then we note that that term cancels with that term. And we note that this term half cancels with that term. And we've got two things left. And if we multiply both sides by 2a, and that's our final equation relating the initial and final velocities and how far you travel for a constant acceleration.